All right, so we're gonna dive deeper right now to the code of the training pipeline. Now, here's the thing, okay? It this seems to be huge. Like when you're starting with something and that you did not build, it feels like a huge mountain to climb trying to understand all of that code. I promise there is nothing uh, complex about this, okay? Every decision that was made here was made one at a time. It's like you build anything. This is not me coming and at the same time just putting a bunch of pieces together. So it's not that complex, not that many lines. I think the training pipeline, which is the biggest one, has 509 lines. So and a bunch of those are comments. So it's not even that crazy. So in today's video, or this video, not today's video, but in this video, what I want to do is I want to go step by step of this pipeline and try to uncover what I'm doing here. Okay, so I'm going to try to start with this is what this step is supposed to do, and then go line by line and explain why I'm doing that. So hopefully that's going to help you get a better idea, a better understanding of what's happening. Okay, so here is the code of the training pipeline. In the previous video, we saw what the pipeline does and what not. So let me start just with the specification of the class of the pipeline. Here is the line, okay? So I call it training, and it inherits from flow spec, which is what we have to do when we're creating a Metaflow pipeline. So that's a Metaflow specific thing, but it also inherits from flow mixin. Now, flow mixin is a class that I created. Why did I do that? Well, let's look at flow mixin. Here is flow mixin. And you're going to notice that this particular class has one include file property. This include file is a Metaflow thing. It's a Metaflow feature where when you call it, Metaflow at the time of running a pipeline is basically going to grab the data or the file that's pointed that this include file points to, and it's going to put it together with the code of the pipeline in order to run it. So if I'm running this in the cloud, Metaflow is going to include that CSV together with my pipeline as an asset. So when the pipeline runs, the CSV is going to be available there. Okay, so keep that in mind. Now, I have this here in the flow mixin because I'm going to be reusing the same thing on all of the other pipelines. Okay, so I need to use this data set during the deployment pipeline. I need to use this data set during the monitoring pipeline. So instead of repeating myself, I created this flow mixin that includes this property. So now all of my pipelines will have a property called dataset, okay, or an artifact called dataset. Notice that these include files. The name is going to be penguins. It's text because this is a CSV. This is the help, just text that explain what it does. And the default is pointing to data/penguins.csv. As a reminder, there is a folder here that's called data, and the penguins.csv is going to be inside. Okay. Now, there is also a function that's called, I think that's the only thing that I have, it's called load dataset. So again, this function, because it's part of the mixin, is going to be inherited by any of my flows. And the reason I have this function is because I need to do a couple things with this data set. First of all, there are two ways to load the data in these pipelines. Way number one is just to use the local file. But in a real production scenario, that's usually not the way it works. Okay, so in a real production setting, the data is not going to be just a CSV file. It's going to be coming maybe from an S3 location in AWS, like a place where a bunch of CSV files are going to be copied over. So I'm using a property that's called production, the Metaflow provides, because you can run a flow in production mode or in development mode. So I'm using that property. So when the flow runs in production mode, I'm not going to be using this file. Instead, I'm going to be loading the data from an S3 bucket. Okay. So that's what's going to happen here. So let's look at the code of this load data set. So we try to make sense of what's doing here. So number one, I'm going to ask if we're running in production. Current is a variable that I automatically have available to me because Metaflow has it. So I can just call current. I'm importing it right here. Okay. So I have that available. If we're running in production, I'm going to get an environment variable and I'm going to look for data set. Maybe that was set as an environment variable. If it wasn't, I'm just going to use the value of this property. That's so I can actually change the value just using an environment variable. And then with S3, I'm going to be connecting with S3 and I'm going to be grabbing all of the files that are in a specific location in S3. Basically, if I'm running this in production, I'm going to be using this variable here, dataset, to pass the location in S3. So I'm going to be loading all of the data from that location. And I'm going to be basically, as you can see here, I'm reading a file, or every single file that is in that location. I'm going to read it in memory. And I'm going to create this array with every single file. And then I'm going to concatenate all of those files. So this section here allows me to point my pipeline to a location in S3 and with a bunch of different CSV files, load all of those CSV files and put them in memory together, concatenate them in memory. That's only when I'm running this pipeline in production mode. If I'm not running the pipeline in production mode, then I'm just going to be using this property here, this particular data here to load it directly. So you can see that in that case, I'm just reading one CSV file, which is supposed to be this here. Okay, that's what's happening in this particular line. So this is what the load data set does at the beginning. After doing that, I take care of this data set. Originally, there is one row, I think, yeah, there is one row where the sex column does not specify a value. But it's not that it's empty. Instead, it has like a period, like a dot. So when I load the data set, I'm taking care at this point of replacing that period by an empty value. I'm not deciding right now how I want to handle empty values for that column. I'm going to do that later. At this point, I'm just getting rid of that value because it's not a valid sex. So I'm doing that. And then finally, I'm shuffling the data set. And in order to shuffle the data set, I'm doing two different things, depending on whether I'm running the pipeline in production or not. So if it's running in production, I'm shuffling this data set every single time. It's going to shuffle the data set differently. If I'm not running in production, I'm shuffling the data set always using the same seed, 42, it's just random number. Because this is going to help me reproduce any problems. So I want to make sure in development mode that my data set gets always shuffled at the same time. Okay, so this is what the shuffle does. This line here, line 83, that is what does the shuffle. Expects a random state generator. The state generator is the one that uses the seed, so it knows how to shuffle the data. Finally, this load data set returns the data. Okay, so that's what the mixin, does. So anytime I inherit from that mixin, now I have that available to my specific flow, which is great. Okay, so one parameter that I can use here is the accuracy threshold. I talked before about what this accuracy threshold does. I'm going to use this to decide whether to register the model or not. If the accuracy of the model is not above 70%, I'm not gonna even consider registering the model, okay? By default is 70%. You can specify a new value when you run the pipeline because this is a parameter, okay? Now let's start. This is the first function here, the start of the flow. And I'm using 3 decorators, okay? This step decorator is the one you already know. That has to go on every single step of the flow. Then I have a card decorator. And what this decorator does is indicates to Metaflow that I want to have an entry here in the card viewer. So see how I have start right there? So if I don't have a card decorator, I will not get an entry here for that specific step. So there might be steps that you don't care about, like register. Like you don't see the register step. I'm not generating any artifacts that I want to display in the register step. So the register step is not going to have that card decorator. That's why you don't see it right here. Okay. You can also use the card decorator to specify how you want to display things in this viewer. You can customize the data that goes into the viewer, which is great. You can also use the card decorator to do that. All right, so right now I'm just saying, hey, yes, I want a card decorator for that. And I'm specifying environment. And what this tag is going to do, or this decorator is going to do, is going to make this MLflow tracking URI environment variable available to my step. And this variable is really important because remember, we're going to be connecting to MLflow. So we need to understand where MLflow is located. Okay. So I need to pass the location of MLflow using an environment variable. And I'm reading it here. I'm getting it here and making it available to my flow. So I'm saying, hey, I'm going to be using one variable, which is going to be the MLflow tracking URI. And that is coming from an existing environment variable with the same name. And if you don't find that variable, please use this default value. So by default, I'm saying if the system where this pipeline is running does not have that environment variable set, assume that the server is running locally and try to connect locally. And obviously, if there is no server there, this is going to fail. But that's what I'm doing here. Okay, so let's see what's happening inside the start flow. So here, I'm going to create an artifact here with the value of this MLflow tracking URI. Okay, so that value is going to go into this particular variable here, this particular artifact. So I can use it across my entire flow. Anytime I reference this artifact, it's going to have the value that came from that environment variable, which is awesome. All right, so logging stuff. Then I'm setting the tracking URI to the MLflow library. So anytime now I use the MLflow library, MLflow already knows where it's connecting to, okay? So that's why I set it to the artifact here, and now I set it to this variable here, okay? Okay, so this is saying if the mode will be production if we're running this in production. If not, we're gonna be in development mode. I'm just displaying here a log saying in which mode we're running. Notice that here we're saying we're loading the data set. So I'm calling the load data set from the mixin that we've already discussed, and I'm saving the result. I'm grabbing the result. I'm creating an asset, which is self.data. That's where I'm saving the data set. If we go to the start here, you're going to see the data is right here, right? You can also see like a view here. See, artifact name data, and it's just my data set. This data, again, is this self.data that I created right here. So that's awesome. So after doing that, I'm going to start a run in MLflow, okay? Now notice that I'm starting a run and I'm providing a name to that run. And that name is the run ID of Metaflow. Current is references Metaflow. I'm taking the run ID from Metaflow. So if I show you here, the run ID is this one here. So it ends on 726. So I'm using this same run ID to start a Metaflow run. That is why in Metaflow, you see this ID here. I could be naming this potato if I wanted to. And if I don't specify a name, Metaflow is just going to generate a name for it. But then it's going to be very hard to match them both. So I wanted to have them connected. That's why I'm using the same ID. And then I'm going to save that, the run ID. I'm going to save it right here just so I can keep track of it and I can keep using it later on, I create an artifact MLflow run ID. Because I'm creating an artifact here, you can always check that in the viewer. So there must be an artifact which is called MLflow tracking, no, not that one, MLflow run ID. You can get it here. This is the ID of that specific MLflow run, okay? Remember, the name is the one that we're setting, not the ID. We're setting the run name to the Metaflow name. That's the value that you see. When you come here, that's the value that you see. And then Metaflow takes care of generating an ID. I don't even know if you can see an ID here. Oh, there we go. Run ID is right here. This ID is the one that I'm saving internally as an artifact. Okay, so what else am I doing here? I'm creating an artifact here with the training parameters. So I'm basically grabbing these two constants. They're coming from common. You can see them training epochs. I'm going to be training my model for 50 epochs, and I'm going to be using a batch size of 32. And I'm setting those here at this level. The reason I'm setting these two here at this level is because I'm going to be reusing this information later on. So I wanted to set it in an asset right here. That's going to make it easier later on. You're going to see that. So because it's an asset, you should see it here. See, training parameters. There you go. So that's getting locked there. And then I finish and I go to the cross-validation and the transform. Now, this is asking me to run two different steps in parallel. And that's what's going to happen. So Metaflow is going to automatically go to cross-validation. And at the same time, it's just going to go to transform. Now, all of this is running on my computer. Well, in this case, it's running in Private IDX right now, which is just a single computer running this. But if I was running this, let's say in Kubernetes, you could run this Metaflow flow in Kubernetes. You could actually have multiple instances running specific flows. If I'm running this in AWS batch, and I'm going to show you how to do that. What's going to happen is that there's going to be one computer running the cross-validation step and another separate computer running the transform step in parallel. So you can run this much faster. You can also design a flow by, linearly, but that would take way longer to finish, obviously. So having the ability to parallelize steps is a huge deal. Okay, so the cross-validation step. The goal of this step is to generate the indices to split the data for the cross-validation process. We're going to be using a 5-fold cross-validation process here. So my goal with this particular step is to prepare those 5 folds. So basically say, okay, so fold number 1 is going to have all of these 4 portions of my data set will be for training, and this 5th portion is going to be for test. Fold number 2, these are the indices. Fold number 3, these are the indices. So basically generate all of that information so I can pass that information to the transform, train, and evaluate folds. Okay, so that's what's going to happen in this cross-validation fold. It's very simple. I just use the kfold class from scikit-learn. Okay, it's going to do all for me. I'm saying, yes, generate 5 splits and shuffle those splits. Then I'm just generating this false property. Let's go here to cross-validation. Look at this. See, I don't have the cross-validation here because I don't have a card for it. So let's fix it. Let's come here and let's do, hey, just generate a card so I can actually see what's getting generated. And let's rerun that pipeline. So because now I have a card here, when it runs, it should display, there we go, this is the start. Let's just wait a second until it finishes the cross-validation. There we go. Now we have a card for cross-validation, and we can actually see what's going on internally. So we have a new artifact that's called false. And here, let's just take a look at one specific fold, okay? Let me see if I can get to a point where, okay, there we go. Yes, so this will be one of the values that are inside. So notice that I have fault number 0, okay, it says the fault number, which is the 0. Then it comes an array containing either the training or the test data, and then another array containing either the training or the test data. I do not remember which one is it, but these are the indices, okay, of the data. And then I do the same thing for the second fault and the third thing for the second fault. And obviously the indices will vary from one fault to the other. That is what goes into faults right here, okay? That's what I'm storing right here. The indices are coming from this enumerate function. This is a Python function that's just creating that. Okay, awesome. So after I create that in the cross-validation step, I'm going to the transform fault, but I'm calling transform fault with a for each, okay? So that means that it's gonna go through the property false, and for each one of the items inside false, it's just gonna call transform fault. Now, if you look here at this fault, and it might be a little bit harder to tell, there are gonna be 5 items inside. So this is an array. Here you get like the square brackets. It's an array, and there are 5 items inside. This is fault number 1 with an index 0, fault number 2, fault number 3, etc., up until fault number 4, which is this final one. So we're gonna be calling the transform fault 5 different times, 1 for each fault, okay? So let's see what happens in transform fault. Here, I'm gonna grab that data. How do I grab the data that comes from the previous step? So because this is a for each, I mean, this step was called from a for each, there's gonna be a property that's called input. And that's part of the Metaflow documentation. You can read how the for each works. But basically, this self.input contains the data that I'm passing to this transform fault, which is basically this, one of the items of this self faults array. So remember, the items contain number 1 is the fault number, then it contains the train indices. So that's the array that we saw here, all of these indices that we saw here. These will be the train indices, and these will be all of the test indices. So train indices and test indices. So I'm basically unpacking self.input into these 3 variables here. That's what I have right now, okay? So I'm gonna be logging that information. So you're gonna see transforming fault, And if we go to the output here, we should be seeing that. Let me go up. You can see it not training, but we should see a transform. There we go. Transforming fault 1, transforming fault 0. See how they're not even in order because they're starting in parallel. So they, each of them start in different orders. Okay, so let's go back to the code. So now that I have all of this information, okay, I'm going to take the target column from the data. Remember, I have access to the data. I'm going to take the species column and I'm going to reshape it so I can actually apply transformations to this. This species column here comes in a specific format, and I'm just doing the reshape so I can actually pass it to a pipeline from scikit-learn. This is just a trick to get data in the format that it needs to go in order for the function to be able to work with it. Not a big deal. Then we're going to be building a target transformer. This is a function that's going to build a transformer to modify that target column. The target column is the species column. Let's take a look at the transformer. So I have a function here. The reason I have a function outside in the common file that is not part of the training pipeline is because I reuse these 2 functions in a pipeline that it's here, but I'm not going to have any explanations for it, but you can check it on your own, which is the tuning pipeline. So there's going to be here a tuning file that does hyperparameter tuning. Again, it's not documented. You can take a look on your own if you wanted to. and I use the build target transformer and build features transformer there as well, because it's across different pipelines. I have them here, so I can reuse the code. So building the target transformer, what this is going to do to the species column is to do an ordinal encoder to the species column. Ordinal encoder will turn the categories, different species, Adelie, Chinstrap, and whatever the other one is, which I don't remember, never remember. I think it's Gentoo. It's going to turn them into numbers. So Adelie will become species number 0, Gentoo will become species number 3, and Chinstrap will become species number 2, whatever the order comes out to be. So the way I do this is just using a column transformer from scikit-learn, and I'm saying, hey, the name of the transformer is going to be species, apply an ordinal encoder here to the first column that comes here. And that is what's happening right here. I'm building the target transformer, so now I can apply that target transformer, and I'm getting the Y column. This is the way I call it, the Y train column. Basically, all of the train data that I have, the Y column, which is the target column, the species column, I'm going to fit that transformer on that train column, okay? So let me go really quick here I don't know if I have a transform. I do not have a transform here. It doesn't matter. But I want you to just spend a second in this line here and in this line, because there are things that are key, very, very important for this to work. So I'm grabbing my transformer and I'm fitting my transformer on the species data. Notice how here I use the train indices to grab the specific rows from the data set that correspond to this particular fold. So the indices are going to say grab row number 1, number 7, number 10, number 27. Those indices, when I apply them here, this will only return the rows with those indices. I'm grabbing that information, specifically is the species information, which is just one column. I'm grabbing that and I'm fitting my transformer on that data. And the return of that is not going to be an array with Adelie, Gentoo, Chinstrap. No, it's going to be an array that's already transformed. So instead of the actual class, I'm going to have an ordinal number. So it's going to, instead of Adelies, I'm going to get 0s. Instead of Chinstrap, I'm going to get 1s. And instead of Gentoos, I'm going to get 2s. That is what I'm going to be saving in this Y train class. So this Y train class now is a vector containing the indices of the species corresponding to those penguins. Notice that I'm using fit transform here. Now for the test data, doing the same thing here, the only difference is obviously I'm going to be pointing to the test indices instead of the train indices. And for the test data, I'm not doing fit transform. I'm only doing transform. Why is that? Well, when you do fit transform, any information that has to be computed by the transformer in order to do its job is going to be computed when you call fit or when you call fit transform. That information is going to be computed, and that information is going to be used to do the transformation. In this particular case, the information that has to be computed is which specific ordinal will be assigned to each class. So if I have an Adelie, Gentoos, and Chinstrap, the fit transform will decide which index to add to each one of those classes. So let's say it decides that Adelies are going to be 0s, Gentoos are going to be 1s, and Chinstraps are going to be number 2. When I call transform, that information does not get recomputed. It was computed already during the fit. So that information is only going to get used. So when it goes to replace Adelies on the test data right here, it already knows that Adelies are number 1. Now, if I do a fit here as well, if I get to do a fit here as well, if I run it like this, the second time I call fit, maybe the ordinal encoder will assign different numbers. So at the least, instead of being number 0, they might become number 1. And now you're going to have a training data set transformed with certain characteristics that are different from a test data set. Because in this data set, addelees are number 0. In this other data set, addelees are going to be number 1. That is not good. You don't want that to happen. So you want to make sure you call fit on the trained data and you do transform only on the test data. So that is what's happening right here. And at the end of it, I already have the Y column, training and testing, ready to go. Now we need to do the same thing on all of the other columns, not on the target, but on all of the other columns of the data set. So for that, I have a build features transformer function here. So let's take a look at the build feature transformer. It's not too complex. So here I'm going to have 3 column transformers. I'm going to start from the one that I return. I'm going to try to unpack it. So there are going to be 2 transformers that I'm going to call in this column. The first one I call the numeric transformer. And as you can see, I have a selector that is going to exclude any columns that are objects. In Pandas, usually columns that are string, that contain string data, they're going to become objects. So this transformer is basically only getting applied to columns that are numeric, because if they're non-objects, they're numeric columns. Okay? So what am I applying here? Well, I'm applying the numeric transformer. So let's take a look at the numeric transformer. So the numeric transformer is a pipeline that first is going to impute any missing values using the average of that column. So if we're talking about the body weight of a penguin, okay, and on average, when you add up all of the values on that column and divide by the number of values, let's say that average is, I don't know, 2,000 grams. That's the body weight. Any missing value on that column will be replaced by 2,000 grams because that's the average of that column. That's what this simple imputer strategy does. And then I'm just doing a standard scaling. By the way, I talk a lot about imputation and scaling during the live session, so you're going to get more information there. But this is just doing a standard scalar using the standard deviation of the column and the mean of the column. So it basically takes any values like the 2,000 and tries to get that value to a number that's very, very small, between a very small negative number and like a slightly larger above 0 positive number. So that's what it tries to do. It squeezes all of the numbers. Instead of having values in 2,000, 3,000, it just makes them 0.77 or negative 0.2. It's like very small number to very small negative number to a small positive number. That's the range that it goes. So that's what I'm doing throughout all of the columns. Why do we do this? We're going to talk about that in the live sessions. Why that's important, we're going to talk about that in the live session. So that would be the first transformation that I have in this transformer. Remember, this only will get applied to numerical columns. Now, for categorical columns, specifically for columns island and sex, those are the 2 categorical columns. I could do something like this as well and have a selector just for object columns. I could do that. In this particular case, it's easy to do. So I just put for the island and sex columns, which are categorical, please apply the categorical transformer to those columns. So this categorical transformer does an imputation here, just like we did for numerical numbers. But in this case, I cannot use the mean because it wouldn't make sense. These are not numbers. The strategy that I'm using is the most frequent strategy. So if the sex is missing, remember, there are going to be some rows where sex is not going to be present. That value is going to be replaced by the sex that's the most prominent on the data set. I think it's male, maybe. So male is gonna be used in those cases. And after doing that, I'm gonna be doing one-hot encoding. So the sex, for example, which is male or female, those values are gonna be replaced by a one-hot encoded vector, which basically one-hot encoding, again, we're gonna be talking a lot about that in the live sessions, but for each possible categorical value, it's gonna create a column on my data set, and that column is gonna either have a 0 or a 1, depending on the value that I had. So what this build features transformer is doing is replacing at a high level for the specific numerical columns is imputing missing values with the average and then scaling all of those columns. And for the categorical columns, what it's doing is imputing the missing values with the most frequent and then applying one-hot encoding to all of those columns. So that is what's gonna be happening here. We are gonna do or follow the same process we followed before for the target column. So I create that transformer. Notice that now I'm going to be creating X-train and X-test. X meaning, well, this is just representing all of the columns. Y is representing the target. Notice how here first I start fitting the transformer and doing the transformation on the data using the indices for the data. And then I'm going to only do the transform. I don't do the fitting again. Remember, you only do the fitting on the trained data. So at the end here, what I just did was have a Y train and Y test, X train and X test artifacts containing the data already transformed and ready to send to a model, to build a model. And that is exactly what we're going to go next. We're going to go from this transform fold onto the train fold. The train fold is right here. This is the step. Couple things happening here. Number one, this step requires an environment variable called Keras backend. And if that environment variable doesn't exist, I'm going to be using the value JAX. So this code uses Keras version 3. Keras is just a front-end library, so basically you can use it to train your model, but you can switch which backend you want to use. By default, Keras comes with TensorFlow backend. I don't want to use TensorFlow here, so I'm using JAX. You could also change and use Torch backend, which is great. So anyway, I need that environment variable. I'm creating it here. If it doesn't exist, I'm setting it to JAX. There is a card here, so this is going to produce the output in the card viewer. And there is a resources tag here, which I have here for illustration purposes only, because by default, the memory assigned to this step is going to be 4 megabytes. That's fine. Nothing is changing here from what I'm doing. This is just to show you something that you could potentially do when you're running this in the cloud. Let's say this training process requires a GPU. You could request a GPU using the resources tag. Let's say you require 10 terabytes of memory. I mean, that's too much, 10 gigabytes of memory. You could request that using the resources tag. And at the time of running this in the cloud, the orchestrator there will make sure that this step runs on a computer with the specific resources that you are requesting. That is extremely, extremely powerful. Remember, not the entire pipeline requires those resources. To transform the data, I might not need a GPU. So I don't want to be paying GPU hours for transforming my data set. Why would I do that? That would be very expensive. Instead, I can just request the resources that I want on the specific step that needs them. So that step will run on an instance with those resources, but I won't be wasting those resources running other steps. That is extremely powerful for Metaflow, And that's what I wanted to show you here with line 180. All right, so this train fault supposed to be very simple. So these few lines here, they just prepare Metaflow and connect to MLflow, sorry. So remember that we had this artifact that we created in the start. It's just the tracking URI that points to MLflow. So I'm setting it here. I'm importing the library, setting the tracking URI here so it connects to the proper place. And then I'm just I'm starting a run, okay? So I'm saying, look at this, look at how I'm doing it. I'm saying start a run with the MLflow run ID, which is the parent run that we already started. And then I'm passing like a sub run, right? This sub run is one that's gonna be called cross-validation fault, and then the number of the fault. That is what creates, if I go here to the MLflow UI, and I open one of these, that sub run is one of these, okay? So I want to track every single cross-validation run separately from the parent one. So you get this tree-like representation in MLflow, which is extremely powerful. Okay, so I'm doing that. Notice obviously that I'm saying that this is nested on the previous one. So within that, anything that I do here, if I call auto log, all of that will get automatically logged to MLflow. MLflow will take care of logging all of the model building, all of that stuff is going to automatically log that, which is amazing because I don't have to do it manually. Okay, so here I'm saying, well, first of all, I'm just going to save this fault run ID. So from different steps, I can keep contributing to that specific run in MLflow. So I'm going to be saving that here. And I'm going to do, please do not log any models. So the auto log, I'm going to turn off logging the models. Why? I don't care about the weights and biases of any one of the specific cross-validated models. I don't care about any of those. I don't want to pollute MLflow with that information. I'm not going to worry about it. Okay, so awesome. So don't do that. And now I'm going to call the build model function. I'm going to show you what that is. So let's go to common. There should be a build model function here, which is the one that's using Keras 3 to create or define a neural network. Now, something that's very, very important. This particular data set, which is a tabular data set, the Penguins data set, you should build a non-neural network to solve that, and you're going to be better off. Like XGBoost will work better for this particular data set than a neural network. Any like a random forest model would probably work, if not better, at least as good as a neural network works on the tabular data set. I'm using a neural network because it's not the point of these videos or class to show you how to build models. I like neural networks. I wanted to show you how to use Keras 3. Normally, bigger data sets, non-structured or unstructured data has to be solved with neural network-based models. That's what I wanted to bring a neural network here. Is more for fun than because it's what you have to do. So the fact that I'm using it, basically what I'm trying to avoid is the question, why did you use a neural network? Well, I used it because I could. That's it. Not because it's the best, but just because I could. And this is a simple enough exercise that a neural network works very well. So let's take a look at our neural network here. It's very simple. It's a sequential. I'm using the sequential function here. So that means it's a fully connected neural network. The input layer is just, I'm passing the shape. And basically the shape is how many columns in that data will be. So I'm going to be passing all of those columns here. That's going to be how many input neurons I'm going to have. Then I have a fully connected layer with 10 neurons using the ReLU activation function. Then another fully connected layer with 8 neurons using the ReLU activation function. And the output layer is going to be a softmax activation function with 3 neurons. Why 3? Because there are 3 possible species of penguins: Adelie, Gentoo, Chinstrap. Because we have 3 possible species of penguin. That's why I'm using 3 neurons here. And it's softmax because I want the output layer, all of those values, to sum up to 1. This is not very common. This is the way you build multi-class classification models. It's nothing new here. Okay, so after defining my model, I'm compiling my model. This is what you do in Keras. You specify what the optimizer will be. In this case, I'm using the stochastic gradient descent optimizer. I'm passing the learning rate to the build model here. I'm using the categorical cross entropy loss, the sparse categorical cross entropy loss, and the metrics that I want to keep track of is just accuracy. So that is my model. That is what the build model function will return. Will give me this model here, which I'm, adding as an artifact. I'm creating an artifact, so I'm assigning it to variable self.model because I'm going to be using this model later on to evaluate it. So I want to use this artifact later on. That's why I'm assigning it here. So after I build this model, I just fit this model using the train data. Here in this case, it's just all of the columns and specifying what the correct target values are. I'm saying verbose 0, so it doesn't just, fill the logs with what it's doing. And then I'm passing here the training parameters, which if you remember, those are the batch size, which is 32, and the number of epochs, which is 50. So I'm passing those here. So this here is just going to train the first version of my model. That's it. And it's going to do that for each specific fold. Remember, we are inside train fold. Okay? So after I finish training my model, I'm just going to go to the next step, which is evaluating this fold. Now, this next step requires the Keras backend as well. So I'm specifying the environment variable here, so I get access to it. You're going to see that in this step, I'm using self.model, which was created during training, and I'm evaluating this model with the test data, with the X test and Y test that I prepared during the transform. Okay, and I'm computing the loss, or I'm grabbing the loss and the accuracy from this evaluation. Okay, I'm logging that information, and then I'm going to log that information into MLflow. So setting the tracking URI in MLflow, every time I use MLflow on a separate step, remember that step might be running somewhere else, might not be in the same computer, it's definitely not in the same portion of the memory here, that variable is gone. So every time I import it, I need to be setting the tracking URI so it connects exactly what I needed to connect. So I'm setting that tracking URI to my server. I'm starting a run, which is the sub run now. This is the MLflow fold run ID. So this is pointing to like this cross-validation fold 4, for example. And under that, I'm logging test loss and test accuracy. You can use log metrics to log anything you want. So if I go into one of those, let me go into one of those, we should see in the metrics, the test loss and the test accuracy are logged right here. Those two metrics I logged here. So that is good. That's what I wanted to do. So finally, after I do this, after I evaluate this and log that, I'm just going to go to the evaluate model. So this is taking me out of the forage. Okay. So if we go to the DAG, you will see that after the evaluate fold, I just go out of the forage. This is not part of the forage anymore. This is a join step. So it's a join step because it's joining, has to wait for everything that happened before it, all of those forage, all of those folds, has to wait for all of them to finish, and they all gonna join into this evaluate model fold. So you can read more about in Metaflow how those work. But this is taking me out of the forage. And notice how this step now expects an inputs. Inputs is going to contain all of the artifacts that were generated in the previous for each steps, okay? So I can do stuff with them. So let's see what happens here. So first of all, I call merge artifacts, and this is a Metaflow thing. Now, here's what happened, and look at the comment. We need access to the MLflow run ID and MLflow tracking URI artifacts that we set at the start of the flow. So remember, those two artifacts we set here at the start of the flow, okay? But we are now here in this evaluate model fold. And in order to make sure all of those artifacts go through this for each and get included into the data that I have access to, I need to do a merge. So I'm doing a merge artifacts, the inputs which come from the for each, and I want to include the MLflow run ID and the tracking URI that were generated before, okay? Because if you keep reading the comment, it says, since we are in a join step, we need to merge the artifacts from the incoming branches to make them available. If I don't do this, I won't be able to access MLflow run ID anymore because I'm in a join step after the for each. So I do the merge. I'm going to get access now to these two, which is awesome. So this here is going to compute the final evaluation. So it looks a little bit scary. It's not. So I'm going to go for every single one of the inputs that I got, and I'm going to be grabbing the accuracy and the loss from those inputs. Remember, all of these inputs is auto-generated by Metaflow, and what goes into inputs are all of the artifacts that I created during the for each steps, okay? So obviously there is an artifact called accuracy that I created there. Remember here, there we go. I created an artifact called accuracy, and I created an artifact called loss. So when I go through all of those inputs, there are going to be 5 of them because we had 5 for each steps. I'm going to be grabbing the accuracy and grabbing the loss and adding them into this metrics array. And when I have that array of arrays, I can just compute the mean, and the mean is going to give me, for one column, will be the mean of the accuracy, and the other column will be the mean of the loss. So I'm going to get the accuracy here and the loss here, and those are the average accuracy and loss. And I can also do the same thing for the standard deviation. I'm using NumPy here, obviously, backup to compute the mean and the standard deviation. I can also do the standard deviation here to compute the accuracy standard deviation and the accuracy standard loss. Very simple. So I'm going to print them out here. So we're going to see if we go here, we should see them somewhere. There you go. So you're going to see accuracy 0.94 with a plus minus 0.05 standard deviation. And you're going to see the same thing for the loss, which is great. And after I do that, I'm going to be connecting to MLflow to the parent run, MLflow run ID, and I'm going to be logging those metrics, these 4 metrics, the cross-validation accuracy and the cross-validation standard deviation, accuracy standard deviation, the loss, and the loss standard deviation. And I'm logging these here in the MLflow run ID, which is the parent one, not one of the fault ones, but the parent one. If we go there and we open the parent one, in the metrics, we should get these metrics logged, which is awesome. Okay, so we're almost through this. This portion here is the evaluate model. Now, this is going to go to register model. Okay, so if we go to the DAC, this evaluate model goes to register model. But we cannot open register model unless we finish the transform and the train model. Now, fortunately, these 2 steps are very simple because we already saw them here. But instead of worrying about the data from a fold, these 2 steps work with the entire data set. So let's take a look really quick at what they do. This is the transform step. Again, this is going to apply the transformations to the entire data set. Notice that here I'm not using any indices to select the data that I want to transform. I'm just creating a Y vector containing all of the species already transformed, and I want to create an X matrix containing all of the features that I want to transform. I'm not applying this now to a test data because I don't have test data here. This is just applying the transformation to the whole data set. And from there, I go to the train model section, which again, we saw this before. It's very similar to the one before, except this here, again, is not logging the model. I don't want to log this model. Now, this is the model that I care about, but I'm not auto-logging the model here because I'm creating a custom model. We're going to talk about that later. So that's why I'm asking MLflow, please do not auto-log the model. So I'm building my model, okay, using the same function that we saw before, and I'm fitting my model on the X and Y, the X matrix and the Y vector. Here I'm displaying some logs. So those are the logs that you see right here. That's just training the, the final model or the big model. I'm passing the same exact training parameters than before. I'm logging these parameters. So when I train the full model, I just log those parameters. So if we go here, we should see those parameters somewhere logged. There we go. So here are the parameters. So there should be a batch size. There we go. Batch size is 32, and there should be an epochs 50 right here. So I'm logging those parameters. Everything else, you see all of the other parameters, those are auto-logged by MLflow. MLflow, see the optimizer name, SGD, all of that is auto-logged by MLflow. MLflow knows exactly how Keras works, knows how to do that, which is great because I don't have to log all of that information for myself. So after I finish training my model, now I can go to register. So again, register is coming from the train model. Let's go to the DAG. Register is being called by the train model, and it's being called by the evaluate model. So register is a join step in Metaflow, okay? So I'm gonna get that inputs parameter there. So if we go to register, you can get the inputs parameter here. I'm merging the artifacts, so making sure all of those artifacts are merged now and I have access to them. And this is what's gonna register my mod. So let's see what's happening here. This is the final step. So first, I'm going to check the accuracy. Remember, I do not want to register a model if it doesn't have an accuracy above a specific threshold. So if the accuracy is not above that threshold, I'm not going to do anything here. I'm just going to log a message saying that the accuracy is not high enough. And that's it. And I'm done. Okay. Now, assuming the accuracy is good enough, I'm going to set the tracking URI for MLflow. You saw that before. I'm going to start a run with the main run. And here I'm also creating a temporal directory. And the reason I'm creating a temporal directory is because I'm going to be saving stuff inside that directory. Now, look at this. This is how I'm logging them on. I'm using the MLflow pyfunc.log model. This is a function that is going to allow me to log a custom MLflow model. Now, why is this? And again, there is a separate video which is going to talk about this because we have to go and see what this model class contains. I'm going to show you here the model class really quick, high level. It's called inference, the file. So this is the model that we're going to be deploying. It's 250 lines. It's not nothing. And I have to explain how that works. But for now, understand this. What comes out of the Keras model that I train, that is just weight and biases. And that's it. That's what it is. And that model, remember, is going to be expecting a number of inputs, a vector of inputs, and it's going to be outputting a softmax vector. That's awesome. But we need a little bit more than that in order to deploy and make it available to different applications. For example, this model only works with information that was previously transformed. Remember, we did that here. in order to train a model, we first had to transform that information. So if I deploy that model the way it comes out of Keras, I'm going to be forcing every single client of that model to transform that information before using the model, which is crazy. It's too much work. They don't have to do that. I might change my mind later, and I'm going to break every single application out there. So I don't want to expose that interface to my clients. Also, the output of that model, the one that comes out of the Keras model, is just a softmax vector. So it's going to be a vector with 3 values inside. And anyone using that model will have to know how to interpret those 3 values, right? They will have to know they have to do an argmax to get the highest class, and they will have to know what the ordinal of the classes are. So if the answer is 2, they have to know that corresponds to Chinstrap. So it's pain in the neck. I don't want to deploy that model. Instead, I'm going to be creating a custom, a wrapper around that model. And that wrapper is the one that I'm going to be deploying. That wrapper will help me do a bunch of different stuff. We're going to show that later, including creating a proper interface for a model that expects a JSON, beautiful JSON, transforming the data internally, getting an output, and transforming that output before I present it to a client. So that's why I need a custom model here. So I'm going to do that, and I'm going to lock that model using this line 419, the lock model function from MLflow. And this is all of the information that I have to pass here. Okay, so let's go one by one and see what happens. The Python model is the class that I'm going to be, that contains the code of this wrapper. And we're not going to go into that class right now. We're going to see it in a different video, but know that that class is just a class that I created that defines the interface and the output and all of that of the model. So I'm passing that instance right here. The name that I'm going to be using to register the model is Penguins. That's why here in MLflow, when we go to this column that says models, you see the version, the model name Penguins here. Okay, so the artifact path, so where is the artifacts going to be located? I'm saying in model code path, that is the code that needs to be packed together in order for this model to work. Like I mentioned, the implementation of this model class is in this file called inference. So that's why I'm specifying, hey, just grab the inference file from, my source code. That is the file that you have to pack together in MLflow in order to reconstruct this model. Now, what are the artifacts that are going to be attached to this model? I'm calling a function, and we're going to see what that function does. Get model artifacts, and I'm passing it the directory, the temporal directory that I created. So let's go to that function. Here is the function. And this is going to return the list of artifacts that will be included with the model. Okay? The model must pre-process the raw input data before making a prediction. So we need to include the scikit-learn transformers as part of the model package. Remember, this new model is going to be receiving JSON. So it's going to be expecting a sex column. But in order for us to pass that sex column into the actual neural network, we have to transform it using exactly the same transformations pipelines that we created during the training process. So what's happening here is that I need to pack together with the model. I need to save packed with that model the transformers that I created during the training process, so I can reuse those transformers during inference time. That is what the get model artifacts is doing. It's basically grabbing, number one, you can see here, is grabbing the model and saving it, okay? Let's say I have a directory here, okay? So it's saving the model to that directory, but it's also saving the feature transformer and the target transformer that we created before, is also saving them into that directory, okay? Notice how I'm dumping using joblib. Joblib is a library that is going to dump these transformers in the joblib format. And I'm saving the features transformer and the target transformer. These are artifacts that exist at this point. I'm saving them into this path, which is inside the directory folder. Okay, so what I did here is grabbing features transformer, target transformer, and model.keras and saving that. Those are the three assets that I need to pack with my model. Okay, so what am I returning here? Well, I'm returning the model, the feature transformer, and the target transformer. That's what I'm returning. I'm passing it to the log model here. So this is going to know where to find those files. It's going to go to that temporal directory, grab those files, and upload them to MLflow. So if I go here to MLflow, and I open this, and I go to artifacts, you're going to see these artifacts. You're going to see the three files that I just talked about. The first one is the features.jotlib. This is the features transformation pipeline. The model.keras, that's the actual weights and biases of the model, and the target.jotlib, which is the target transformation pipeline. Those are the three artifacts I'm packing together in order to create a model. Without those three, I don't have any model. Okay, so I'm passing that. What are the PIP requirements? Like, in order to run this model, what are the libraries that MLflow needs to install? And I'm calling a function. And this is just a function that's just going to return, hey, what is the function? It's right here. For this model to work, just grab scikit-learn, grab pandas, grab numpy, grab keras, and grab JAX GPU. And remember, this is coming from packages. Packages is a function that I created in Common. I think I already explained that before, but there is a function that I created in Common that I pass a list of names, and it grabs the name and the version from this constant. And in this constant here, I have all of those names and the specific version I want to install. Now, something that might happen to you by the time you're watching this video, I might have changed one of these versions, maybe bump it up a little bit. You can also do that on your side. That's fine. Just keep in mind that every time I'm referencing one of those libraries, I'm using the packages function that grabs the specific version as well. That ensures that whenever I run these, it actually has the requirements that I need to install. Okay, so this is what the get model PIP requirements has. Let me go back up. Finally, it's just the signature of the model, and the signature helps people that are going to be installing that model understand what that model is about and how it works. So I have a function for that, and that function is just calling the infer signature from MLflow, and I'm passing an example input. This will be an example JSON input to my model, okay? And I'm passing an example output. This is just an example, and I'm letting this infer signature come up with the actual signature, okay? And then there is a params here. I'm going to explain these params later on, but this model will support parameters. In this case, there is a param which is going to be data capture. I'm going to explain that later, but if we go to MLflow here, if I open this ML model, this ML model contains the whole definition of my model. And you go to the signature, notice how the input signature of this model, okay? And it's in a specific format. It's an array with type and name and require, and all of that is getting automatically inferred by the example that I provided to that function. The outputs, the parameters, all of that good stuff is right here. Also, remember, if I go, I think I have to go to, let's go to model register here. Yes, so if I go to the specific model, this is version 3 of the model, you get the schema here, you get what the values are, you get them here, the type. This is another representation of that signature. It's just a table here telling you what that signature is. Description, I don't have any description. You can add tags. I don't have any tags. All of that good stuff. All right, so that is what the register step does. And if we go to the DAG, the register step is the one that comes right before the end. So let's take a look at the end step. It's right here. the end step, the only thing that it does is just printing out saying, hey, the pipeline finished successfully. Everything else are the functions that we already talked about. Obviously, this is just the execution that you have to do, the main section of the file where you call the pipeline. So this is how the training pipeline works. After seeing this, if you go back to the README file and you go back to this diagram might make a little bit more sense. So yeah, hopefully it explains everything that I did, and I'll see you in the next video.